I want to tell you about something that has puzzled physicists, philosophers, and anyone who thinks deeply about the nature of reality for nearly a century now. It is a rule, or perhaps I should say a principle, that lies at the very heart of quantum mechanics, and yet it defies every intuition we have developed from living in the macroscopic world. This is the measurement problem, or what I sometimes think of as the peculiar, unavoidable role that observation plays in determining what is real. Some call it the collapse of the wave function. Others speak of it in terms of complementarity or the uncertainty principle. But whatever language we use, we are circling around the same strange, inescapable fact. In quantum mechanics, the act of measurement does not merely reveal reality, it participates in creating it. Let me start with a confession. When I first began working on the structure of the atom, back in 1912 and 1913, I did not fully appreciate how radical the implications would be. I was focused on solving a specific problem: how to reconcile Ernest Rutherford's nuclear model of the atom with the laws of classical physics, which predicted that such atoms should be unstable and collapse in an instant. My solution was to propose that electrons could only occupy certain discrete orbits, certain stationary states, and that they would not radiate energy while in these states despite being in accelerated motion. This worked beautifully for explaining the spectrum of hydrogen and many other phenomena, but I was still thinking, in some ways, in classical terms. I imagined electrons as little particles following definite paths, even if those paths were restricted to certain allowed orbits. It was only later, as quantum mechanics developed through the work of Heisenberg, Schrödinger, Born, and others, that the true strangeness of the quantum world became apparent. And the weirdest rule, the one that still troubles people today, emerged from this deeper understanding. Let me try to explain it in a way that does justice to both its strangeness and its profound importance. In classical physics, the physics of Newton and Maxwell, the world operates according to deterministic laws. If you know the initial conditions of a system, the position and velocity of every particle, you can in principle calculate its future state with perfect precision. A billiard ball rolling across a table follows a definite trajectory determined by its initial motion and the forces acting upon it. Even if we cannot measure these quantities with perfect accuracy in practice, we assume they exist. The ball has a position and a velocity at every moment, whether we measure them or not. Quantum mechanics tells us that this picture is fundamentally wrong at atomic scales. A quantum particle, an electron for instance, does not have a definite position and momentum at the same time. This is not merely because we lack the instruments to measure both quantities simultaneously, as if we were just too clumsy or our tools too crude. Rather, it is because these quantities do not exist simultaneously in any definite sense until we perform a measurement. Before measurement, the electron is described by a wave function, a mathematical object that encodes probabilities for where the electron might be found if we look for it, what momentum it might have if we measure that instead, and so forth. The wave function, which we typically denote with the Greek letter psi, evolves according to Schrödinger's equation. This equation is deterministic and continuous. If you know the wave function at one moment, you can calculate it at any future moment. There is nothing mysterious or probabilistic about this evolution. The wave function spreads out smoothly through space and time according to precise mathematical rules. But here is the crucial, strange part. The wave function itself does not tell you where the electron is. It tells you where the electron might be. The square of the wave function's amplitude at any point in space gives you the probability of finding the electron there if you measure its position. Now, this might not seem so strange at first. Perhaps you are thinking that probability simply reflects our ignorance. That the electron really is somewhere definite, and we just do not know where until we measure. This was Einstein's view, and it was the view of many physicists who felt uncomfortable with the new quantum mechanics. They imagined that there must be some deeper level of description, some hidden variables that determine where the electron actually is, and that the wave function merely represents our incomplete knowledge of these hidden realities. But this interpretation, comforting as it might be, is wrong. We know it is wrong because of countless experiments that have been performed over the decades. Experiments that test the predictions of quantum mechanics against those of any theory based on hidden variables. The experiments consistently support quantum mechanics and rule out the classical picture. The electron genuinely does not have a definite position before we measure it. It exists in what we call a superposition of multiple possible positions simultaneously. This brings us to the weirdest rule, the measurement problem itself. When we measure the position of an electron, we always find it at a specific location. We never measure it to be in two places at once. The measurement gives us a definite outcome. But before the measurement, the wave function describes the electron as being potentially in many locations. So what happens during the measurement? How does the electron go from being in a superposition of multiple possible positions to being definitely at one specific position? This transition is called the collapse of the wave function, and it is unlike anything else in physics. The evolution of the wave function according to Schrödinger's equation is smooth, continuous, and deterministic. But the collapse is instantaneous, discontinuous, and probabilistic. The wave function, which was spread out over a region of space, suddenly collapses to a single point, or at least to a very localized region, when we perform a measurement. Which specific location does it collapse to? We cannot say with certainty. We can only calculate the probability of each possible outcome. The electron might appear here with probability 30%, there with probability 50%, somewhere else with probability 20%. But which outcome actually occurs in any given measurement is fundamentally random. It is not determined by any prior state or hidden variable. It is genuinely, irreducibly random. This is what disturbed Einstein so deeply. He believed that physics should describe reality as it is, not merely predict measurement outcomes probabilistically. He felt that if quantum mechanics required this kind of randomness and discontinuity, it must be incomplete. There must be some deeper theory that would restore determinism and tell us what is really happening when we are not looking. His famous declaration that God does not play dice with the universe was his protest against this fundamental randomness. I understood Einstein's discomfort. I shared it to some degree. But I came to believe that his objections were based on inappropriate expectations about what physics should be. Physics, in my view, is not about constructing a picture of reality, as it exists independent of observation. Physics is about what we can measure, what we can predict, what we can know through interaction with the physical world. If we cannot, even in principle, observe certain properties simultaneously, if the very act of measurement affects what we measure in a fundamental way, then it is meaningless to insist that those properties exist in some definite form behind the scenes. Let me give you a concrete example that illustrates the measurement problem vividly. Consider an electron that we have prepared so that its wave function describes it as being in a superposition of two locations, let us say location A and location B, with equal probability. Before we measure, the electron is not at A and not at B. It is in both places simultaneously, in a sense, though we must be careful with our language here. It is not that the electron is somehow divided between the two locations. Rather, the electron is in a state that has no classical analog. It is in a superposition that will manifest as either A or B when we perform a measurement. But until that measurement occurs, it is either. Now, suppose we place a detector at location A. If the electron is there, the detector will click. What happens when we turn on this detector? According to quantum mechanics, the wave function collapses. If the detector clicks, the electron is now definitely at A, and the part of the wave function that was at B simply vanishes. It does not travel from B to A. It does not gradually shift. It instantaneously ceases to exist in any meaningful sense. If the detector does not click, then the electron is now definitely at B, and the part of the wave function at A has vanished. This is deeply weird. The detector at A somehow affects what happens at B, even though there is no physical signal traveling between them, no force acting across the distance. The collapse appears to be instantaneous and non-local. Einstein called this spooky action at a distance, and he thought it showed that quantum mechanics must be wrong or incomplete. But experiments have repeatedly confirmed that nature really does behave this way. The measurement problem becomes even more puzzling when we consider what counts as a measurement. Does it require a conscious observer? Is the detector itself sufficient, Or do we need a human being to look at the detector? What if we replace the detector with a cat, as Schrödinger famously did in his thought experiment? He imagined a cat in a box with a vial of poison that would be released if a radioactive atom decayed. According to quantum mechanics, before we open the box, the atom is in a superposition of having decayed and not decayed. Therefore, the cat should be in a superposition of being alive and dead simultaneously. This sounds absurd, and that was Schrödinger's point. He was trying to show that quantum mechanics, taken literally, leads to nonsensical conclusions when applied to macroscopic objects. My response to this paradox was to emphasize the role of complementarity and the importance of specifying the experimental context carefully. In quantum mechanics, we cannot talk about the properties of a system in the abstract. We must always specify how we are measuring it, what apparatus we are using, what questions we are asking. Different experimental arrangements reveal different aspects of reality, and these aspects may be complementary, meaning they cannot be observed simultaneously but are all necessary for a complete description. The boundary between the quantum system and the measuring apparatus is crucial. When we perform a measurement, we are not simply observing a quantum system from the outside. We are creating an interaction between the quantum system and a macroscopic apparatus that amplifies the quantum behavior into something we can directly perceive. The measuring apparatus must be described classically, using definite properties and deterministic behavior, because that is the language we use to communicate our results. The quantum system, on the other hand, is described by a wave function and superpositions until the measurement occurs. Where exactly does this boundary lie? This is one of the deepest questions in quantum mechanics, and I confess I do not have a completely satisfying answer. In principle, we could treat the measuring apparatus itself as a quantum system, with its own wave function that becomes entangled with the system being measured. But then we would need another apparatus to measure the first apparatus, and so on. At some point, we must adopt a classical description. We must speak of definite outcomes, of pointers pointing to specific numbers on dials, of records being created that can be shared and discussed. This is what I mean by the necessity of classical concepts in quantum mechanics. We cannot eliminate them without losing the ability to communicate about what we have observed. The weirdest rule, then, is this: measurement forces a quantum system to choose one of its possible states, collapsing the wave function from a superposition to a definite outcome, and this process is fundamentally random and irreversible. We cannot predict which outcome will occur in any individual case, only the probabilities of different outcomes. And we cannot separate this rule from the practice of physics itself, because physics is ultimately about making measurements and comparing predictions with observations. Let me return to the double-slit experiment, which Richard Feynman rightly called the central mystery of quantum mechanics, because it illustrates the measurement problem so clearly. When we send electrons through two slits and let them hit a screen on the other side, we observe an interference pattern, alternating bands of high and low intensity. This proves that each electron behaves like a wave, passing through both slits simultaneously and interfering with itself. But if we place detectors at the slits to see which one each electron goes through, the interference pattern disappears. We get two simple bands on the screen, as if each electron went through one slit or the other like a classical particle. What is happening here? Before we place the detectors, each electron is in a superposition of going through both slits. This superposition allows interference. When we introduce the detectors, we perform a measurement that determines which slit the electron goes through. This measurement collapses the wave function, forcing the electron to choose one slit or the other. Once the electron has been localized to a specific slit, it can no longer interfere with itself, and the interference pattern vanishes. The crucial point is that we cannot have it both ways. We cannot observe which slit the electron goes through and also observe the interference pattern. These are complementary aspects of the electron's behavior. Depending on what we choose to measure, we see either wave-like or particle-like behavior, but never both simultaneously. This is not a limitation of our instruments. It is a fundamental feature of nature. The electron does not have a definite path through one slit while also exhibiting interference. It genuinely behaves differently depending on whether we measure its path or not. Some people find this troubling because it seems to give human observers, or measuring devices, a special role in determining reality. It sounds almost like idealism, the philosophical position that reality is fundamentally mental or dependent on consciousness. But I do not think this is the right interpretation. The key is not consciousness but interaction. A measurement is a physical interaction between a quantum system and a macroscopic apparatus that creates an irreversible record. It does not matter whether a human being observes this record. What matters is that the interaction has occurred and that the quantum system has become entangled with the macroscopic world in a way that leaves a definite trace. In my discussions with Einstein, I often emphasize this point. Physics is not about what exists independent of observation. Physics is about what we can know through observation and measurement. Einstein wanted a theory that described reality as it is, whether anyone looks at it or not. I argued that this demand is based on a category mistake. We are not outside the universe looking in. We are part of the universe, and our observations are physical interactions within it. The act of measurement is not separate from the physical world. It is part of the physical world. And quantum mechanics tells us that certain types of interactions, those we call measurements, have the special property of collapsing superpositions and creating definite outcomes. Over the years, many physicists have tried to avoid or eliminate the measurement problem by proposing alternative interpretations of quantum mechanics. Some, like David Bohm, develop theories with hidden variables that restore determinism and give particles definite trajectories even when we are not measuring them. These theories are mathematically consistent and make the same predictions as standard quantum mechanics, but they require introducing unobservable entities and mechanisms that seem, to me at least, unnecessarily complicated. They are trying to save classical intuitions at the cost of adding complexity. Others, like Hugh Everett, propose that the wave function never collapses at all. Instead, every time a measurement occurs, the universe splits into multiple branches, one for each possible outcome. In one branch, the electron is at location A. In another branch, it is at location B. All outcomes occur, but in different parallel universes that cannot communicate with each other. This is the many worlds interpretation, and while it is elegant in some ways, avoiding the need for a special collapse process, it seems to me to multiply entities beyond necessity. Do we really need to postulate an infinite number of parallel universes that we can never observe just to avoid accepting that measurement plays a special role? I remain convinced that the Copenhagen interpretation, as it came to be called, is the most sensible and economical way to understand quantum mechanics. Yes, it requires us to give up certain classical intuitions. Yes, it places measurement in a special position. Yes, it embraces fundamental randomness and complementarity. But it does so in a way that is faithful to the mathematics of quantum mechanics, consistent with all experimental evidence, and honest about what we can and cannot know. The weirdest rule in quantum mechanics is weird because it challenges our deepest assumptions about how nature works. We expect reality to be definite and independent of observation. We expect that if we could just look closely enough, we would find particles with specific positions and momenta, following definite trajectories. We expect determinism and locality, the idea that things only affect each other through direct contact or signals traveling at finite speeds. Quantum mechanics tells us that all of these expectations are wrong at the atomic scale. But this is not a defect of quantum mechanics. It is a revelation about the nature of reality itself. The universe is not a clockwork mechanism with gears and springs that we can take apart and examine piece by piece. At its most fundamental level, the universe is quantum, probabilistic, non-local, and deeply interconnected. Measurement is not passive observation but active participation. We do not stand outside nature looking in. We are part of nature, and our interactions with quantum systems are woven into the fabric of physical reality. I think about these questions often, even now. What is the nature of measurement? Where exactly does the quantum world end and the classical world begin? Why does the collapse happen? What determines the moment of transition from superposition to definite outcome? These are profound questions, and I do not pretend to have answered them completely. Perhaps future generations will develop deeper insights, new mathematical frameworks, or new experimental techniques that illuminate these mysteries further. But I also think we must be careful not to demand more from physics than it can provide. Physics is wonderfully successful at predicting what will happen in precisely defined experimental situations. It gives us mathematical tools of extraordinary power and precision. But it does not necessarily give us intuitive pictures that satisfy our desire for visualizable mechanisms. At the quantum level, nature resists our attempts to fit it into familiar categories. The sooner we accept this, the sooner we can appreciate the true depth and beauty of quantum mechanics. The weirdest rule, the collapse of the wave function, the special role of measurement, is weird precisely because it is genuinely new, genuinely different from anything in classical physics. It is not merely a technical detail or a mathematical convenience. It is telling us something profound about the structure of reality. It is telling us that the universe does not exist in a definite state until measurements occur that create definite records. It is telling us that potentiality and actuality, possibility and reality, are more intertwined than we ever imagined. It is telling us that the observer and the observed cannot be completely separated, that knowledge and reality are bound together in ways that classical physics never anticipated. When I worked out my model of the atom more than a century ago, I thought I was solving a puzzle about energy levels and spectral lines. I did not realize I was opening a door to a completely new understanding of nature. One that would challenge every intuition developed from everyday experience. The journey has been strange and difficult, full of debates and confusions and gradual clarifications. But it has also been immensely rewarding. We have learned that the universe is far more subtle, far more interesting, far more mysterious than we could have guessed. The weirdest rule in quantum mechanics is weird because reality itself is weird, at least when viewed from the perspective of classical physics and common sense. But perhaps we should not call it weird. Perhaps we should simply call it quantum. This is how nature actually is. Our classical intuitions, developed from experience with macroscopic objects moving at slow speeds, are the approximation, the special case that emerges when quantum effects average out and become negligible. The quantum world is the fundamental reality, and the classical world we experience is built upon it. So when I say that measurement collapses the wave function, that observation participates in creating reality, that quantum systems exist in superpositions until we measure them, I am not proposing anything mystical or arbitrary. I am describing what decades of theoretical work and experimental verification have taught us about how nature operates. It is strange, yes, but it is true. And coming to terms with this strangeness, learning to think quantum rather than classical, learning to accept complementarity and randomness, and the special role of measurement, is the price we must pay for understanding the atomic world. This is the weirdest rule in quantum mechanics, and it is also, in many ways, the most important. It is the rule that separates quantum mechanics from all previous physics. It is the rule that forces us to rethink what we mean by reality, observation, and knowledge. It is the rule that makes quantum mechanics quantum. And while it may never feel completely comfortable or intuitive, while it may always retain a quality of strangeness and mystery, it is the gateway to understanding nature at its most fundamental level. And that understanding, strange as it may be, is one of humanity's greatest achievements.